Hello everyone, in this video we're going to start talking about module 1, atomic structure. Before we get into actual atomic structure, we want to introduce a few basic concepts we're going to use a lot in the content of this class, such as liquid, solid, and gas. We all probably know that there are three physical format matters can exist in normally, okay? Solid, which occupies space, has a certain shape, has a mass. Liquid, which also occupies space, has mass, but it doesn't have a fixed shape. The gas has mass, it occupies space, but it does not occupy a certain amount of space. It depends on the container. Now, obviously, it doesn't have a fixed, certain shape either. So that's kind of easy to understand. And also from point of view of chemistry, we would like to categorize matter into three levels, okay? Elements, compounds, and mixture, okay? I would like to use some examples to show you what they are really. Before we talk about these three things, let's look at this periodic table. The periodic table basically is a summary of all of the elements. Okay, so each one of these symbols, okay, inside each one of the block represents one kind of element. So basically, this whole universe is made of by these elements, nothing more than this. You might see some different color code of different elements. That's something else we can talk about later. But for now, you just need to understand there's so many different kinds of elements. Okay, now the individual elements. Okay, let's say the individual unit of elements is usually called atom. Okay, so let's say using a circle representing hydrogen atom. Okay, so if you have one of the hydrogen atom here, so that's we say it's a hydrogen atom. Okay, if you have multiple atoms of hydrogen together, okay, atoms, so let's say one circle represents one atom, then we say okay, they both belong to a hydrogen element. Okay, they both belong to a hydrogen element, this category. You may also have hydrogen atoms, two of hydrogen atoms kind of chemically bond together. So the connection here, so between two hydrogen atoms, there are chemical bond. Okay. Then we say this is a hydrogen H2 molecule. Okay, so you see the difference between atom and molecule is atom represents one atom, and molecule is represented usually has multiple atoms in it. Okay, a multiplicity here could be two or more than two, but either one. Okay, as long as you contain only one kind of element, in this case they're all hydrogen element. There's nothing else like any other elements. Then we say okay, the combination of all of these are still going to belong to element or a hydrogen element, particularly in this case. Okay, the key information here is there's no other elements. You can have hydrogen atoms or hydrogen molecules, but both are hydrogen elements. All right, the next level is when you have different kind of elements and bond together, then you would have a compound. All right, compound is composed by not only multiple atoms, but also multiple elements. All right, keep in mind the hydrogen molecule here, they're composed by multiple hydrogen atoms, but there's only one single kind of element. Whereas compound, for example, water, okay, the formula of water is H2O, which represents there are two hydrogen atoms. Okay, let me use circle representing hydrogen atom. Let me use another triangle representing the oxygen atom. Okay, the O here is the symbol of oxygen. Let me use a triangle here represents the hydrogen atom. Okay, now there's a chemical bond between the hydrogen and oxygen, and there's another chemical bond between the oxygen with the other hydrogen. So this makes the fixed composition of water, which is water molecule. So because there are two different kinds of elements, okay, so water molecule belongs to the category of compound. Okay, you may have multiple water molecules. Okay, as long as they all have the same composition, HHO, HHO, then we say this is a compound. Okay, now if you mix up the compound with different compounds, different elements together, you would have what we so called, which is also mostly commonly seen in our daily life, which is called a mixture. Okay, let's say what kind of mixture we can have. First of all, you can have a mixture of different elements. Okay, let's say you have a hydrogen atom, you have an oxygen atom, triangle shaped. You may have multiple hydrogen atoms or multiple oxygen atoms. Then we say this is a mixture. Now you have to realize that the difference between this mixture and this compound we referred earlier is H2O is a fixed composition where you have chemical bond, okay, connecting H2O, HHO. Whereas here, there's no chemical bond. Okay, two hydrogen atoms and two oxygen atoms, they are simply mixed up together. There's no chemical connection between them. Okay, so that's a mixture. You may also have a mixture between, for example, between hydrogen molecule with oxygen molecule. Okay, this also representing two different elements mixed up physically, not chemically. You may also have hydrogen atom with water molecule. That's also considered to be a mixture. Okay, so you can see, let's summarize what we just said. Okay, the essential difference is pure elements is simple. If you have only one kind of elements, no matter what, then you are a pure element. Compound, you have more than one kind of elements, but the ultimate unit of this chemical is molecule, the same kind of molecule. So this is a molecule, this is a molecule, this is a molecule. Then we say it's a compound. Notice that each molecule containing different elements. Okay, mixture. If you mix up elements or compounds then you're basically making a fake mixture. Okay, so most of the time we see it every day. Okay, it's mixture. We barely see anything that's pure elements in our daily life. So talking about mixture, okay, we're gonna further introducing a couple more concepts here. Usually we distinguish heterogeneous mixture and homogeneous mixture. By name, you probably can tell that the difference between heterogeneous and homogeneous is a homogeneous mixture is what you probably not able to distinguish the components of the mixture. It looks like one thing. That's why it's called homogeneous. Heterogeneous is the opposite. You can easily see or identify the components in the mixture. Okay, the classic example will be salt water. If you put the salt into water, if you dissolve salt into water, the salt was solid, but once you get into water, it looked like it's dissolved, it's disappeared. So the salt water looked like just water. You can't really see where the salt went. So that's homogeneous mixture. If you put something like sand into water, they can be mixed up, but you can still see the sand, suspended in the water. So you can see two different things in the mixture of sand and water, and that's called heterogeneous water. So homogeneous water mixture is basically, it looks like one thing even though it's a mixture, whereas heterogeneous mixture, you can see different things in the mixture. Okay, your first experiment, first lab is going to be dealing with some mixtures. You have to tell whether they are heterogeneous or homogeneous. Sometimes you even have to start by identifying whether they are a mixture or not. They may not be a mixture. They may be a compound or elements like that. Okay, so following this, we would like to introduce a couple more things, such as physical and the chemical properties. All right, let's. I copied the slides over here so we can play around with our drawing board. So typically, okay, physical property usually are the property you can see, you can feel about some chemical, okay, such as how does it smell, what color does it look like, what volume does it occupy in space, is it a solid, liquid, or gas? This kind of physical appearance they usually belong to physical property. Physical properties also include density, melting point, and boiling point. They are also physical properties. Whereas chemical properties sometimes is not as obvious as physical properties. Okay, chemical properties usually mainly refer to the reactivity of this compound. What is reactivity? Well, it's basically how sensitive this chemical is, or how easy this chemical is to react with other chemicals. Such as if you have a piece of metal, okay, steel, iron, and that, and in the moisture, especially in Florida temperature, does it get rusted? So rusting of steel, that's a chemical. It can easily rust. That's a chemical property. If you eat any food, taking any nutrition into your body turn them into either energy, turn them into nutritious supply to your body. That's digestion of food. That's a chemical property of the food. So chemical property are usually how this chemical, either an element or compound, can react with, whether they react or not, or if yes, how would they react with other chemicals. That's usually chemical reactivity or chemical properties, which is usually not as obvious as the physical property. So of course, any change to physical property, okay, then we say it's physical change. Any change to chemical property, well, then we say it's a chemical change. Physical change is simple, okay. If you change the color, if you change the volume, if you change it from solid to liquid to gas or the other way around, those are usually considered to be physical change. A typical example is if you melt ice into water, that's a physical change. If you boil water into moisture vapor, that's a physical change. If you condense vapor into back to water, or freeze water into ice, these are physical change. Okay. Now, or if you have a piece of metal, okay, you cut into two halves, you bend it. Those are changing the shape, changing the size. Those are also physical change. Okay. If you, for example, if you mix yellow plus blue, and you come out to be green, it's a color change, but it's a normal color change because yellow plus blue you should give you green. So that would be also considered a physical change. Now, what is a chemical change, or how do we know it's a chemical change or not? Okay, the essential difference between the chemical change and the physical change is the physical change does not change the chemical itself. For instance, ice, the chemical composition of ice is H2O. The chemical composition for water is also H2O. The vapor of moisture is also H2O. So no matter how you change the physical format of H2O, they are always H2O. You're not changing what what this molecule is. Okay, it's just the way how these molecules aggregate together in the gas phase, in liquid phase, or in solid phase. So that's physical change. Physical change, it does not break the molecules, does not break things, or does not change the things essentially are. Whereas chemical change, okay, you can imagine, is totally opposite. For instance, if you pass electricity, okay, into water, and you can break this water, liquid water, okay, doesn't matter actually, into hydrogen gas, excuse me, plus oxygen gas. Now this is a chemical change, because you can see the actual molecule of water now is destroyed. Okay, the actual water molecule is no longer H2O anymore. The H2O is gone. You now have another two different kinds of molecules, hydrogen and oxygen gas. So this is a chemical change. You are breaking up this original molecule. You're changing this chemical into something else. Okay, so that's a chemical change. Usually, okay, the physical change is more obvious. Like we said, it changes the shape, it changes the color, sometimes you change the temperature, so you can easily feel it. Whereas chemical change is not as obvious as it is. So how do we know if it's a chemical change or physical change? Let's put it this way, okay. If you see physical change observations, you see all kinds of things, odor change, phase change, color change, those are observations, and you believe those are just normal physical change? You don't believe there's anything chemically has been changed, or you don't believe the chemical has been different, then you say, okay, that's a physical change. Okay, sounds very obvious. Now you can also have some physical change, such as I see the color change. I see something that's white. After a while, it turns into green. Now you may say, okay, that's a physical change, but that's a physical change normally wouldn't happen. That's a physical change indicating the chemical is actually now different. Okay, so you see physical change accompanied by chemical change. Okay, you see both. You see physical change, and you also believe that physical change is caused by a chemical change, then you should identify this as a chemical change. So what I'm trying to say is, seems like I'm making that sounds like the chemical change is kind of superior than physical change. In some way, it is. Okay, so the physical change, if it's a physical change only, then you identify to be physical change. Okay, if you believe there's a physical change, but it's kind of normal physical change, such as if you decompose water into hydrogen gas and oxygen gas, so you see bubbling gas coming out, you would say, okay, that's some physical observations, but I believe there's a chemical change behind it. So I would say, okay, that's a chemical change. Okay, so yeah.